who are we? We find that we live on an insignificant planet of a humdrum star, lost in a galaxy tucked away in some forgotten corner of the universe, in which there are far more galaxies than people. But the cool thing is, everything out there is made up of the same stuff we are, and it's about time we start learning about them. At the beginning of the 20th century, Albert Einstein revolutionized the way scientists think about space and time. Einstein realized that space and time are relative. An object in motion actually experiences time at a slower rate than one at rest. Now, this may sound absurd to you, but because we small humans travel incredibly slow compared to the speed of light, we just don't notice the delay in time when we're running, driving, or just moving. Einstein looked further into this and came to the conclusion of the fabric of space-time. That vast emptiness you see in space can actually be thought of as a geometric field. Einstein published his theory of general relativity in 1916, explaining that what we perceive as the force of gravity in fact arises from the curvature of space-time. For illustration, take a look at this setup. Picture the cloth as the fabric of space-time. As objects with large amounts of mass are placed onto the field, they create indents in space-time. These weights can be seen as the planets and stars of our universe. So, what happens when other things of matter are put onto our fabric? That's right, they're drawn to the object pulling down with the largest amount of mass. So, although Earth appears to be pulled towards the Sun by gravity, there's no such force. It's simply the geometry of space-time around the Sun telling the Earth how to move. Just for kicks, let's try a heavier weight. See that? That's what happens in space when a mass is extremely immense. That, friends, is a black hole. So, what exactly is a black hole? They're not solid objects, but rather regions of space with very special properties. Matter or light can enter a black hole, but nothing that enters can ever return. Furthermore, they have such a strong gravitational pull that everything, even light, gets sucked in.
So if light is being pulled in, why do they call it a black hole?
Good question, Maeve. They call it a black hole because light is neither emitted nor reflected from it.
But if black holes don't emit or reflect light, then how do you see a black hole?
Good question, Cindy. You see a black hole by looking at the effects of gravity on its surroundings. Also looking at X-rays emitting really hot gas. And also looking at the stars orbiting unseen masses. That's about it. Now, you may be wondering how a black hole is formed. Could one appear close to Earth and suck us all into an unavoidable doom? No. The common black hole starts off as a dying star. Throughout a star's life, there's a constant tug-of-war between gravity pulling in and pressure pushing out. Nuclear reactions in the core of the star produce enough energy and pressure to push outward. For most of a star's life, gravity and pressure balance each other out, and the star is stable. However, when a star runs out of nuclear fuel, gravity gets the upper hand and the material in the core of the star is compressed. Eventually, in a smaller star, the repulsive forces among electrons create enough pressure to halt further gravitational collapse. The star then cools and dies peacefully, being known as a white dwarf. When a very massive star collapses, it causes a supernova, or exploding star. Outer parts are blasted into space, while the remaining core completely collapses under its own weight. Unlike smaller stars, it does not have enough repulsive forces to overcome the enormous amount of gravity, thereafter creating a black hole. Now don't worry, our sun won't meet an avoidable fate as a black hole and suck us all up, destroying humanity and all our solar system. The sun doesn't have enough mass to collapse into a black hole. In 4 billion years, when the sun is at the end of its life, it will fade into a white dwarf, just like 90% of the other 200 to 400 billion stars in the Milky Way. The anatomy of a black hole is fairly simple. Right at the core is the singularity. This is the center of a black hole that everything gets sucked and compacted into. It has a radius of 0, but an infinite density. The event horizon is the region of space that is the boundary of a black hole. Think of it as the point of no return. Anything past this point would need an escape velocity greater than the speed of light to get out. And because nothing can go faster than the speed of light, even light cannot return from the outside world past this point. The Schwarzschild radius of a black hole defines the event horizon. Hypothetically, anything could become a black hole if it was compressed past its Schwarzschild radius. If you fill out the Schwarzschild radius formula for the average human adult, you would get 9e to the negative 26 meters. That's right. To become a black hole, you would need to be smaller than a proton. The Earth would need to be the size of a peanut, and the Sun would need to be the size of a small town. Black holes, well, they're a little larger. A mid-range black hole would have the mass of about 1,000 suns and be the size of Mars. A supermassive black hole, like the Phoenix cluster, would have a mass of 20 billion suns. Something else worth mentioning is Hawking radiation. In quantum mechanics, if a reaction is possible, the opposite reaction is also possible. This is a simple and obvious law of our universe, and before Stephen Hawking, black holes defied that law. Black holes suck everything in, but nothing can ever come out, right? Wrong. In 1976, physicist Stephen Hawking provided a theoretical argument proving black holes can exist. He defined Hawking radiation, the emittance of tiny subatomic particles and photons from the event horizon of a black hole. This means a black hole can fade away. If you were to turn into a black hole, you would dissipate in 2e to the negative 11 seconds. If you were going the speed of light for that long, you would only go 6 millimeters, whereas black holes in our universe would require a much, much longer time. Furthermore, black holes are constantly sucking particles in, meaning they balance their own rates of dissipation. They're not going away anytime soon. Stephen Hawking once said, "I used to think information was destroyed in a black hole. This was my biggest blunder, or at least my biggest blunder in science. Black holes hold so much information about our universe, and it's imperative we keep studying and learning more about them." Evidence suggests that most, if not all, galaxies have giant black holes at their cores. Here's the supposed location of Sagittarius A, the black hole at the center of the Milky Way galaxy. It is thought to have the mass of 4 million suns. Scientists also believe that supermassive black holes play an important role in the formation of galaxies. Here's a map of the discovered black holes in our universe. Hopefully this documentary taught you something you didn't know about black holes and about our glorious universe. Keep researching.